Start again. We'll have the pleasure to hear Jonas Schober talking about existence and analytic behavior of just solutions for Schrödinger operators on the discrete line with varying spectral multiplicity. Thank you.
Thank you. So thank you for the organizers for also organizing this part of the conference here in Mexico City, especially to Miguel. And I think having two conferences dedicated to Volker's birthday shows how much people, including me, appreciate you. So congratulations again. The talk today is more or less about the same subject as I talked in Merida, but you will not have to sleep because there is new parts. So, but we'll see that in a minute. Okay, so. First, I will give you like a general outline of what one wants to do in scattering theory. Then I will present you my concrete model, and then we will see how we can follow this general scattering theory outline for the concrete model. So let's start. We want to look at dynamics in a quantum mechanical system, and usually there one has a given Hilbert space, which is the space of states, and then a state is a vector in that Hilbert space. And then the time dynamics is modeled by some unitary one-parameter group generated by a self-adjoint operator on that Hilbert space. And then the state at time t is e to the minus ith times the vector one started with. Okay. Now, what is the idea of scattering theory? The idea is to take this real dynamics of the system and compare it to a somehow simpler dynamics or free dynamics that one usually knows more information about. And what does it mean comparing this? It means to look at this limit here. So one takes the dynamics of the free Hamiltonian H0 and kind of place it against the dynamics of the interacting Hamiltonian, and then one is interested what happens when one goes to either plus or minus infinity time-wise. You notice that here I project to the absolute continuous spectrum of H0. The reason for this is that if one wants to have a chance that these limits here exist, well, if one would have an eigenvector to H0, then this limit would just exist if it's simultaneously an eigenvector to the free, interacting Hamiltonian, and well, then it kind of decomposes and nothing interesting happens. So we call these operators omega plus and minus. And then the question is, when do they exist? And there's many results about that, but the one we will use is the Kato-Rosenblum theorem, which says that if the difference of those two operators is small in the sense, for example, that it's trace class, then these operators exist, and in fact they define partial isometries from the absolute continuous spectrum of H0 to the absolute continuous spectrum of H. Okay, if these operators exist, then one defines a scattering operator, which is basically taking the adjoint of one and composing it with the other, which kind of relates the data at plus infinity to the data at minus infinity. Well, if H0 has purely absolutely continuous spectrum, then this here is just the identity. And then the Kato-Rosenblum theorem guarantees that this operator is a partial isometry from H to H, so it's a unitary operator. Okay. Now, one can easily check that this operator commutes with the free Hamiltonian. So that means that if one decomposes the Hilbert space with respect to the spectrum of the operator H0, so it's kind of diagonalization, but in general for infinite dimensional Hilbert spaces, well, we will have a direct integral. Then S decomposes is diagonal with respect to this decomposition. So for every energy E, there exists an operator, unitary operator SE, such that S can be written as a direct integral over these operators. Okay, and these operators are called the scattering matrix with respect to this energy E. We will later also want to prove some kind of Levinson theorem, which means that you first show that this map E to SE is in some sense differentiable, and then once you have that, you look at this logarithmic derivative of the determinant of that matrix, and one kind of wants to make sense out of this integral and calculate its value. Okay, so this is like the general outline of what we want to do. Now let me introduce our concrete model. So we take some integer L and normal matrix A, L times A matrix. This is the input of our model. And then we consider the free Hamiltonian H0 to be defined on the L2 space over the integers with vector valued with dimension L, and it basically relates says that the value in one point n, you take the values in n and n plus n minus 1 and n plus 1, so it kind of relates the one point to its immediate neighbors. We look at this model from a purely mathematic interest, but if you want to imagine something in a physical way, you can imagine a one-dimensional crystal where the atoms are placed precisely in the integers, and then L would be something like the local degrees of freedom, like a spin or something, and then this says that every atom interacts with its two adjacent neighbors. Okay, so this is the free Hamiltonian. Now I have to explain what's the interacting Hamiltonian, and for this we introduce a potential, which is just you put a self-adjoint matrix in every integer, and one wants to have that they have a certain growth condition, which is this. So it's you take the first momentum of the potential and multiply it with some exponentially increasing basis, which is given in this way by the matrix A. We will later see that this is optimal. So one cannot have at least for what we are doing, you cannot have a weaker growth condition on the potential. To have scattering theory, it's sufficient that it's trace class, which would be just that the potential is summable. But for defining the Yost solutions, this is actually necessary. Okay, and this is a potential, and then we just define our interaction Hamiltonian to be just the free Hamiltonian plus this potential. And as I already said, if this condition is certainly weaker than having just being summability, and this is we being trace class. So we're in the realm of Kato-Rosenblum theorem. So all the operators we're interested in exist. Okay. Now the first thing we want to do is kind of simplify our model without losing any information. So since A is a normal matrix, one can do a polar decomposition, and we get the same unitary operator if we polar decompose from the left or from the right. Call that matrix U. And then we define a unitary on the whole Hilbert space, so L2 of the integers, where just in the nth position we multiply by U to the n. And then one can calculate if you conjugate the free Hamiltonian with this unitary operator U tilde, then you basically get the same expression as we get for the normal free Hamiltonian, but now the phase is removed, and we just get the absolute value of A. And we can do the same with the potential and basically get the same potential just conjugated by U to the n. And well, these two calculations together show that if we replace A by the absolute value of A and the potential U by this conjugated potential, then we basically get the same system. They are unitary equivalent, so we can just from the beginning assume that A is a positive matrix. Okay, and notice that these two this tau, what was the basis of the growth condition, is unchanged by this transformation, and also the norm of the potentials is unchanged, which means that this growth condition is invariant under our transformation, so we can also put a check on that. Further, we can make one more simplification, which is since A is a positive matrix, it's certainly a diagonalizable. which means that after a certain change of basis, we can assume that it's diagonal. And then further, we can assume that after another change of basis, that the diagonal elements are ordered by size, where A1 is the biggest and AL is the least. They don't have to be strictly less. We can have one eigenvalues with more with strictly more than one multiplicity. Okay, so this is the model we will be working with, but everything would apply to the general model by unitary transformation. Okay, now as the title of the talk suggested, we want just solutions. So let me talk about generalized eigenfunctions. So the idea is, I mean, in general, H0 has absolute continuous spectrum, so there are no eigenvectors in the Hilbert space, but maybe if one enlarges the space a bit, then we can find solutions to the eigenvalue equations. So let K either be H0 or H and take some complex energy. And we now look in general from matrix valued solutions. So we take some integer n, and then we write Gn Ke for the space of solutions from functions going from the integers to the L times n matrix, such that the generalized eigenvalue equations K times psi is phi is E times phi. So in a natural way, you can write the same expression for functions like this. It's not necessary they have to be in L2. Now, how big is that space? Well, any solution is uniquely determined by the value in two adjacent integers, for example, 0 and 1, because, well, one has this equation with this extra term for the interaction Hamiltonian, and then you see that you can calculate the value at n plus 1, but if you have the values in n minus 1 and n, and the same the other direction. So a solution is uniquely determined by these values, and if you give the values in two points, then you always can realize a solution that has these values, so that the dimension will be 2 times L times n. Okay. Now we want to construct concrete solutions to this eigenvalue equation. And well, let's do an ansatz. So suppose we have some, we will first construct solutions for L times L matrices, and then we look at a general n later. So let's take any invertible matrix Z, and then we just suppose that we get solutions of the form Z to the n. Okay, that's why I need invertibility, because I also have negative exponents. Okay, well, one can just see what happens if I apply the free Hamiltonian to a solution to a function like this, and it turns out, yeah, well, you get this expression here. You get A times Z plus Z inverse times the solution. So if we want this to be a solution to the eigenvalue equation, then, well, one would have to have that A times Z plus Z inverse is the energy E times the identity. So, well, we will have to analyze this function Z plus Z inverse is W. And well, formally it has these two solutions just by solving the quadratic equation. But, well, I'm writing square roots here, but we are in the complex plane, so one has to be very careful about which square roots to use. So let me formally introduce the square roots that we'll be using, and then with this we can construct our solutions. Definition, well, square roots generally exist on simply connected domains where we have no zero. So the simply connected domains we are using is, I denote them by C sigma m, where m is any subset of the real numbers. And maybe better than looking at this formal definition, it's easier to look at pictures. So if, let's say the set m is just m1, m2, m3, then what you do is basically you take out the negative for sigma plus, you take out the negative lines going to minus infinity, and for sigma minus you take out these lines going to plus infinity. And you can do that for any set m. Now, which is the square root? So I want to consider, well, we basically take out the negative imaginary axis and the positive imaginary axis. Then this is a simply connected domain where we can define a square root, and we have just a 0 and 0, so there's no problems with holomorphy. Okay, doing this, we define now our function z sigma, this is precisely the expression we we saw before solving the quadratic equation. And well, we have two roots here, so we have to exclude these lines going down from minus and plus 2, or going up for the other square root. We always do both parts, since in the end we want to cover the whole complex plane by both, so we get a solution for any energy. And then, well, if you do this, then this does precisely what we want to do, so it solves the equation we wanted to have. And well, there's always two solutions. If you have a solution, then 1 over z is also a solution, because that follows immediately from the equation. And this I chose here minus. There's also the one with the plus, and it turns out if you choose the minus, then yeah, it is in a way that on here the absolute value is strictly less than 1. On the interval from minus 2 to 2, it's precisely 1, and down here it's strictly bigger than 1. And well, you always get two solutions, and it turns out that you really always get two solutions, except if you're in these 2 points. Well, then one of the squares is 0, so you get one solution with double multiplicity. Okay, this was for the scalar valued. Now we transfer it to the matrix valued picture. So it turns out that now we have to take out more points, and the points we have to take out is 2a1 to 2al, and minus 2a1 to minus 2al, and then so the set where we define these matrix valued roots are precisely on these sets where we take out here all these lines going from twice the spectrum of A. And well, the matrix version is just we take the diagonal matrix, where on each diagonal we take the scalar valued function z sigma and scale it by these vectors a1 and al. And it turns out if you do that, when we get precisely what we want, we get this equation that A times Z sigma plus Z sigma inverse is E times the identity. And this is designed in a way that here outside we have absolute value strictly less than 1. Okay? So given these matrices, we can now construct some explicit general eigenfunctions. Oh, I just took an example so that you see that they don't have to be different. Generally, can be anything, just not 0 because it's invertible. Okay. Okay. So I mean, we designed precisely these functions Z sigma in a way that if you take them to the power n, this gives us a generalized eigenfunction. And then, of course, if Z is a solution, then 1 over Z also. That's why I want to look at solutions that have prescribed behavior at plus and minus infinity. So I introduce a sign here, which is given by tau. And then if you want, if you want all solutions, well, we have to complement this by so this gives us L different solutions, but we need 2L because that was the dimension of the space of solutions. So we have to complement that. And well, the idea is just to take the ones that turn the other way around. So with a minus sign here. The problem is if you're precisely in one of these thresholds, so 2 times AK for some eigenvalue of k, well, this gives you twice the same solution. So you have to tweak this equation a bit. So in the space of so we take the k such that precisely we are one of the thresholds. If we're outside that, well, we take just the solution we just talked about, and in the orthogonal space to that, well, the other solution is given basically by the same solution, but you multiply it with n. So we have a solution that grows linearly. And then, well, the theorem is these two span the whole space. In which sense? So if you have a general n and an energy E that is contained in this set where we take out these negative lines, then the whole space of solution is given by taking this matrix valued solution, multiplying it by a constant matrix, plus taking these solutions and multiplying it by a matrix here. So these two solutions in some sense span all the solutions. They can all be written as linear combinations of these two solutions. So we now completely understand the space of generalized solution to the eigenvalue equation. Okay, so this is for the free Hamiltonian. Now let's go to the interacting Hamiltonian. So they will not exist on the whole set where we take out these lines, but on a set big enough. Remember that the only thing required in the end is that the sets on which exist solutions, the two of them cover the whole complex plane. So, well, the theorem, Jost solutions are is the name for solutions to the generalized eigenvalue equations for the interacting Hamiltonian. Then the theorem says that there exists at least a subset of one of these two spaces, such that what? Such that at least the upper half plane, oh, that should be set sigma. For minus, it's the lower half plane, and the real line is contained in that set, and that every point except of these thresholds, so A is the 2A1 to 2AL, that this is covered. Maybe these equations here are not so giving such a good picture, so I drew it. So what's happening is you have, so O sigma is this, the red set you see here, so it contains all of the upper half plane. Actually also you can choose it such that it contains everything that's outside of the most outer eigenvalues of A. And then I said that the real line is actually contained in here. And this should actually be the inner points of O. So you can slightly extend it here to the lower half plane, which results that you actually have all the real line to be inner points except these threshold points. And then the theorem says that on this set, you can find solutions to the interacting Hamiltonian. Defined by what? Precisely that if you take the quotient with the solutions to the free Hamiltonian, that this converges to infinity. So at infinity or minus infinity, they look precisely like the solutions to the free eigenvalue equations. And you can do the same for this solutions psi, which was the complementary solutions, and you find also solutions to the interacting equation. And this can be done in a way such that the map that maps E to a solution evaluated at some point n is holomorphic on the inner points of this set. Also, especially in all of the real line besides the thresholds. That's why we wanted to have this slight extension, so we get inner points on the real line. And so this is outside of the thresholds, but later we also want to have some analysis on the thresholds. In general, there it will not be holomorphic, but you get something very close. You get that you can write locally the energy, the solution in some point x as the solution in the point in the threshold, plus not like for holomorphic solutions we would have x minus e, but well there we have this this term with the square root, so we get that it looks like the solution in E plus x minus e times some continuous function f. So you have expansion not in x minus e, but in square root of x minus e. Okay, so so we have these Jost solutions, and now let's see how we can maybe a quick sketch of the proof. So what we want to estimate is these. I'm just considering the case of the solutions phi and not a complementary one, but they can be done more or less analogously, and just the case at plus infinity. Well, you want to somehow estimate this quotient here, and one can then show that well, U is supposed to be a solution to the eigenvalue equation, and we want this Fn, this quotient, converges to 1, and one can show that these two conditions here are equivalent to having this equation. How can one see this? Well, basically one has that Fn somehow is supposed to be the identity, and then one has to somehow correct with these terms in order to make sure that it's a solution to the eigenvalue equations. These coefficients here are precisely chosen in a way so that this works. Also notice that this is implicitly defining f because it appears here and also here. But if you can find a solution f to this, then it satisfies these two properties. How can we see that this is fulfilled? Well, the difference between 1 and Fn is precisely this sum. And if we can somehow show that this is converges uniformly, then, well, if you send n to infinity, the sum goes to 0, so the difference goes to 0. And how you do this? Well, you somehow you have to estimate what's here in the sum, and it turns out that the supremum over all energies in one of the two half planes of this term times this term actually exists, and is precisely a constant times j times this basis that we defined in the beginning to the power j. And this is actually an equality, so the supremum is not less than that, but it is there. So this shows why we actually have to choose this growth property. Like it cannot be done weaker, because otherwise this sum here would not converge. And well, then one shows that in having this, well, we know that the sum over these terms here converges. So if we take n large enough, this sum will be small. So we have a small perturbation of the identity, and then you have 1 is the identity plus this perturbation times f, and so if it's a small perturbation of the identity, one can invert it, and then you get f to be 1 plus this small operator inverse times the identity, and that's how you solve the solution, and then you get these two properties. So that's roughly the outline of how you prove this. The difficult part here is proving this, which is very hard, but can be done. Okay. So now I want to take what we learned about the Jost solutions and use it to prove some kind of Levinson theorem, as we saw in the beginning, which was calculating this integral over the logarithmic derivative. For this, I introduced the Wronskian. So if you have two functions, not necessary solutions, we define their Wronskian in point n to be I times, well, first you evaluate one in n plus 1 and compose it with, take the scalar product with the other in n, and then you switch the roles and take the difference of these two. And it turns out that if you have solutions, one to the energy E and the other to the energy E conjugated, then this is actually independent of n. So from now on, if we have the situation, I will just omit this n here because it's anyway independent of that. And well, we have this Wronskian in general for functions, and well, we can just plug in the Jost solutions that we just proved that exist, and we call this short WE theta. One for the, yeah. I think if you just yes, maybe with some caution, but I think if you don't look at linear combinations of U and V, then you can somehow combine. So it's positive definite on these solutions U and negative on the one spanned by V. So you can have combinations that are weird, but if you just look at U times a vector, then this should be true. But then if you define the solutions with some, like if you switch the sign in one, then it should be fine. So if you tweak it a bit, yes. Okay. Okay. So what does this have to do with the scattering matrix? Well, it turns out that if you, as we said before, decompose the operator S into these scattering matrices, then you can actually calculate the determinant of these scattering matrices in terms of these Wronskians of the Jost solutions, where we prove that exists. One approaching from the lower half plane, and one taking the ones from the upper half plane. And well, you have this correcting factor, which is just, oh, I didn't introduce this. This is the dimension of the bounded solutions to the eigenvalue equation. But that's just some constant factor. We are anyways just interested in the logarithmic derivative. Well, if you take this and plug it into these expressions, well, a constant just cancelled out, and the logarithmic derivative of a quotient is the difference of the logarithmic derivatives. So we can express this expression we are interested in terms of a difference of these Wronskians. And well, and since the Jost solutions are holomorphic on the sets we are interested in, well, which especially includes this interval from -2a to 2a, because we extended it slightly to the other half plane, then we can actually show that SE is also analytic outside of the thresholds and outside of some set that's some finite set where things can get wrong, but outside of that, everything is fine. Okay. Also, this equation up here I forgot to mention also just is valid outside of a finite set. Okay. Now we actually want to calculate this integral over the logarithmic derivative, and to explain you what's on the other side of the equal sign, I have to introduce some objects. So, well, we have the just solutions coming from the upper and from the lower half plane, and in general they don't have to coincide. But there could be vectors for which they actually do coincide, and we call this space V plus minus. We get one for minus and one for plus infinity. And then we take, this is just vectors in C to the L, and then we take the corresponding solutions. So taking our solutions and multiplying by these vectors, this is a subspace of the solutions. This we denote by this H plus minus of E. And then we set HE to be the ones at plus infinity intersected with the solutions at minus infinity. If you cannot imagine so much from these equations, that's basically the solutions that either at plus or minus infinity look like a constant. Well, and look like a constant, it can also look like 0. And it turns out that, well, the kernel, so actually not generalized eigensolutions, but literally L2 functions, well, at plus or minus infinity, they look like 0 because they're square integrable. And it turns out that you can show that the kernel is actually a subspace of HE. I mean, at both plus and minus infinity, they go to 0. So this is certainly a subspace of here. And one can even show that if you're outside of the thresholds, then it's actually an equality. So just in the thresholds, the space we defined here is actually different to the kernel, but it will play a role. So let's define, well, JBE, so JB for bounded, for bound states, the B, is just the dimension of the kernel. And then in general, well, this space H is in general bigger. So let's define JH for half bound states as, well, the quotient of these two, dimension of the quotient of these two spaces. This is for every energy E, we can do that, and then we can just sum these up over all the real numbers. And well, this sum is actually a finite sum because it can just appear in the thresholds and in the eigen energies of the Hamiltonian, which can be shown to be finitely many. So this is a finite sum. Everything is well defined. Okay, now that we have this, let's go back to our Wronskian. Well, we had the expression of the Jost solutions in terms of this. They can locally written as a constant term times the square root term, and it turns out you can just move this to the Wronskian. I mean, it's defined from the Jost solutions, and it turned out that the determinant of the Wronskian can be written can be locally expressed in terms of the square root, and it turns out that if in the energy E you have bound solution, and every bound solution creates a 0, and the order of this 0 is precisely 1 for every bound solution. So we get a term Z minus E to the number of bound solutions, and the half bound states, they create also zeros, but of order a half. So they give me these terms Z minus E square root to the power of half bound states times some continuous function f that's not 0. So the order of zeros is precisely a half times JH plus JB. Okay, so if we take this, then we can calculate this logarithmic derivative of the Wronskian, just plugging this here in. And then, well, what we're interested in is taking integrals of this, and it turns out, well, if you take this expression and take an integral over a closed circle around that energy E, well, this constant just goes out, and the integral over 1 over Z minus E is just 2 pi I. So we can evaluate these integrals over a circle around that point. Okay, now I give you the Levinson theorem. So it's basically saying that you can make sense out of this integral over a logarithmic derivative, and it gives you precisely the number of bound states plus a half times the number of half bound states minus L, which is the dimension of the degrees of freedoms. What do I mean by this limit? Well, sigma ACH0 epsilon is just, you take basically the whole absolute continuous spectrum, but you take out an epsilon interval around the thresholds. So this integral is supposed to be understood as some principal value. And then you make epsilon smaller and smaller. Okay, how do we prove this? Just quickly, well, the logarithmic derivative of the scattering matrix can be expressed in terms of difference of the logarithmic derivative of the Wronskians, as we saw before. And this means that the left-hand side here is equal to integrating the logarithmic derivative of the Wronskian among the following path. So for W minus, we had a positive sign. So on the bottom, we integrate on these intervals to the right. We take out these epsilon spheres around the thresholds. And on the top, we integrate to the left because we had a minus sign. Okay. Then the next thing I can do, if I have immersed eigenvalues, one can actually show that you can, in an epsilon sphere around them, the interval goes to zero. The integral goes to zero, so we can also take out epsilon balls around them. And then outside, well, outside you can show that the limits from above and below are the same. So we might as well just integrate there something, because once we go to the left and once to the right, so it cancels out. And we just integrate up to some number r that's chosen in a sufficiently large way such that there is no eigenvalues outside. So for example, twice the norm of the Hamiltonian or something. And then we consider the following closed path. So you always go in straight lines, and then once you approach either an eigenvalue or a threshold, you just walk a small circle around it. And then you continue walking a straight line, small circle, and so on. And then you close that by walking back with the radius a we chose. And this is a closed circle. On this, since we avoid all the thresholds, it's holomorphic. So we have a closed path for holomorphic function, so the integral is 0. And these dotted lines are precisely what we integrated in the slide before, but in the other way, so that it cancels out. So it turns out that the integral we are interested in is actually the integral over all of these circles. And in this, we know what happens. This was this 2 pi I integral that we calculated before. And so now we can prove the theorem. So in all these points, it just gives us counts as the bound solution with half-bound states, which was this local expression of the Wronskian. And then the big circle gives you just the order of the pole at infinity, which can easily, so you sum up all these, which gives you the bound states plus a half times the half-bound states, and it turns out that the order of the pole is precisely L. So this gives you precisely the statement of the theorem. Thank you for your attention.
So, are there other questions? Yes, Vilker.
Thank you. Yeah, that was a beautiful presentation, Jonas. Thank you. I'm wondering about the case when A2 and A3 coincide. I think then you have these also solutions that have a linear growth besides the exponential behavior. You showed this.
Yes.
Does this change the picture with the half bounds? I mean, what are the half bound states? Maybe you can elaborate on this a little.
Yes. So, well, you certainly have the bound states, so L2, and then in the thresholds you have two types. Well, in the EK, so in the component of the entry that's in the threshold, you have two types of solutions. You have the solutions that are constantly 1. I mean, that's precisely when set sigma is just constantly 1. And you have the linearly glowing solution, so that looks like n. And then the half-bound states is the span of all the solutions that look like constantly 1 plus exponentially decaying solutions. But it could be that they are just look like this at one side and not on the other. And the half-bound states are precisely the ones that look like constant plus L2 on one side and constant plus L2 on the other side. So this is half-bound plus bound states, and then the half-bounds are the ones that don't look like L2 on both sides. Does this answer your question?
Yeah, thank you.
Are there other questions?
In your condition for the existence of the just solutions, there is tau A.
Yes.
So this is actually necessary?
Yes. I tried to explain that. Let me see here. Well, maybe there could be a completely different technique from ours to prove their existence. Then I cannot say anything about that. Like in general, for the wave operators to exist, you just need Kato-Rosenblum shot. You just need summability. But if you want to do something just slightly related to what we do, then you need this sum here to be convergent. I mean, that's how we prove it. This is a Volterra type equation. And well, if you solve it, it at least has to be defined as sum. It has to be converged. And it turns out that, well, you take the supremum of over all energies E of this expression, and it is precisely this thing you sum up in the condition. So if you want to relax this condition, then you will have energies E such that this sum does not converge anymore. And it's actually, the supremum is achieved approaching the real axis. So it's not that the supremum is achieved at infinity, then you could just cut off at big energies, but it's actually achieved at the thresholds. So if you somehow relax this condition, then you don't get your solutions anymore close to the thresholds, which is precisely where all the interesting stuff happens. So you need it. This is actually an equality. It's not that our estimates are bad and you could improve them, but it's actually equality. So you cannot in any way improve this estimate.
Thank you.
So are there other questions? If it's not the case, then let's thank Jonas again. And